Yeah. What do you mind the lab last week? Yeah. I'd have to.
When's your last
Okay, sorry for keep you waiting, because it's my first time to use this computer. So it takes very long time to set up.
Oh, yeah.
Okay, so this is the second tutorial session, and in this tutorial session, we'll work together on some of the questions in example sheet 2. Okay. Have you ever tried to work on this question at home? Don't worry, we will work together here. So we usually will start from the question that are regarded as most difficult. So we start from question number 7. Usually the question put at the last of the list would be more difficult. So we start from question number 7. Just spend a little time to work on this question number 7. Okay? And then I will walk you through how to get the answer. Here is a little hint for you. Just let me know if you encounter any problem. One more hint for you. So maybe I explain how to tackle this kind of problem. So we are asked to compute a joint probability. Now this is a joint probability. We observe a sample of 6 numbers as our sample. So the joint probability of our sample is the probability that the first observation is Bn S1, second observation equal to S2, which is 13, the third observation equal to S3 equal to 6, and so on. And to find this joint probability for a random sample, what we need to do is to multiply all the individual probabilities together. Now, according to the question, we have a Poisson population. So each of these probability will be obtained according to a Poisson probability function. So what we need to do is just to multiply all these together. And in the question, it says that lambda can test 2 values, 10 or 12. So we need to do this once for lambda equal to 10, and then do it another time for lambda equal to 12. So the rest will be just the use of your calculator. You need to use the calculator a lot. But usually we'll simplify this general expression first. We have e to the power minus lambda multiplied together so that it will become e to the power minus 6 lambda. And lambda to a particular power of xi, if we multiply them all together, it is just like we have raised the lambda to the power equal to the sum of them. And in the denominator, we are multiplying all these factorials together. According to the question, we have the observed sample. So we can first compute the sum of these 6 numbers. And we find that it is equal to 59. And we can also compute the product. So this should be 6, okay? Of the factorial of them. Now this number will be very large. You can check with your calculator. It is a huge number. So what we need to do is just substitute everything into this simplified form with lambda equal to 10 and also lambda equal to 12. We can get the 2 answers to this question. I don't have the calculator at hand here, so I already got the answer. Take it out. So it is a very small number. It is expected because for a joint probability, we are multiplying a lot of small numbers together. Of course, it will be very small. And if you have a larger sample size, you expect that this number will be even smaller. And we can do this. So these are just routine calculations. So I hope that all of you can get this answer if you work on your own using your computer or your calculator. And the question also asks us to compare these 2 numbers. Which lambda will give us the larger probability? 10, yeah. This number is larger. So what kind of insight can we get from this comparison? Yes?
Lambda is 10.
Yeah, and lambda may not be exactly equal to 10, but if I ask you to guess, I tell you that lambda can be only 10 or 12. Which one will be a more reasonable and educated guess? 10. Because when lambda is equal to 10, we have larger chance to observe the sample. So 10 will be a more reasonable choice as our estimate. Okay? Now, this kind of calculation is very clumsy. We don't like to use the calculator to do it. So that's why you learn R in this course. Now, in R, there is a very nice function for computing this kind of probability. So we have a function named as dPOIS. POIS stands for Poisson. D stands for distribution. So this will calculate the Poisson probability when S equal to 9, when lambda equal to 10. Okay? So this is the probability that for a Poisson distribution with lambda equal to 10, the chance that we obtain an S equal to 9. And of course, in this question, we are not calculating the probability only for S equal to 9. We are calculating S equal to a set of numbers. So we just input a set of numbers. If you still remember what you've learned in the previous tutorial session, you can use C to combine numbers into a vector. So we input a vector to S. Then what we obtain will be a vector of probabilities. Now this will be also put in the solution uploaded to the blackboard. So this will return a vector of probability corresponding to S equal to 9, S equal to 13, S equal to 6, S equal to 8, 10, and 13. Of course, this is still not what we want to get according to the question. What we need to do is to multiply them together. So finally, we use a nice function in R, product. PROD stands for product. It computes the product of the numbers, the elements in a vector. So this is the answer that we just got. So you can check this with your calculation using your calculator. And actually, you can play around with this code. You put 12, lambda equal 12, we get the answer we got before. And you can also try other numbers. 11, 13 is very happy to play around with this because everything will be done by the computer, calculate for us, right? And you will see that the numbers change a lot. And the largest one you will be still lambda equal to 10, right? But actually, I can show you that this lambda will give you a larger probability. So how can we get this number? You will learn later. We call this the maximum likelihood estimate. Is there any question about this question? Okay. Now let's consider the previous, the next question, question number 6. Just spend a little time to work on question number 6. set of numbers. You are asking to compute a set of numbers. Sample mean, we have a nice sample mean. Okay, I will flash your Remember this? We have a nice mathematical result. It is true for any random sample. It is a mathematical fact. For any random sample, the expectation of the sample mean of that random sample must be equal to the population mean. The variance of the sample mean must be equal to the population variance divided by the sample size. This is a statistical property for random sample. Then it holds for any random sample. As long as you have a random sample, this must hold. So in this question, we are asked to find the expectation of x bar, variance of x bar, and according to this statistical property, what we need is to find the population mean and the population variance. And we are already given the population, which is uniform from 0 to 1. So what we need to do is based on the probability density function of uniform from 0 to 1 to find the mean and variance of the population. So you remember this formula? This is how we find the expectation. Expectation of x is given by integrating x multiplied to the probability density function. And the integral is over the whole real line. Of course, this is the general expression to find the expectation. But we have a particular distribution that distributes only within 0 and 1. Outside 0 and 1, the density function becomes 0. So that means in doing this integral for a particular distribution within 0 and 1, we only need to do the integration within 0 and 1. And the density function within 0 and 1 is equal to 1 for a uniform 0-1 distribution. So the rest will be just an elementary calculus problem. Doing this integral, we can find half. Now, this is the population mean for uniform 0 and 1. And this is actually intuitive. You draw a number from 0 to 1. On average, actually it will be at the midpoint. Now for the variance, there is a formula for finding the variance. I hope that all of you remember this formula. If you are given the population, if you are given the population density, probability density, if you are asked to find the population variance, we usually will use this formula. First, find the expectation of square of s, then minus the square of the expectation of s. This is the general formula for finding the population variance. And we already got the expectation of S, which is the population mean, equal to half. So what we need will be expectation of the square. So we need to first start with this intermediate step. And similar as before, we multiply square of S to the probability density function, integrating over the whole range of that distribution. Now, from my past experience, I find that students always make mistakes at this step because they are asked to calculate the variance. So this is the intermediate step, and then they terminate here. Okay. This is not the end of the story. Of course, you also need to make use of this to find the variance. Now, this is also not the end of story of this question because we just obtained the population mean and population variance only. But what we are asked is to find the expectation of the sample mean, variance of the sample mean. So that we need to make use of this general property. And finally, expectation of the sample mean is equal to half. And the variance of the sample mean is equal to one over 120. We have example of size 10. Okay, you read the original question. It says that we have example of size 10, S1 up to S10. Now I would like to say a few words about the meaning of this expectation of the mean of mean, variance of the mean. Somehow it is very confusing. Just imagine that every one of you, I ask you to randomly select 10 numbers uniformly from 0 to 1. You select 10 numbers, you select another 10 numbers, you select another 10 numbers. Every one of you will get a different sample because it's randomly selected. And if each of you compute a sample mean, of course your sample mean will be different from each other. So we have, let's say, 40 sample means here. And there will be some behavior of this sample mean. On average, the average of this sample mean will be the expectation of the sample mean. That's the meaning of this expectation. And as I mentioned before, the sample mean you obtain will be different from each other. How different? The variation, how large is the variation of the sample mean you obtain? And that is this number. That's the meaning of this mean of mean and variance of mean. It tells us the behavior of the random quantity we obtained from the random sample. Okay? Is there any question? Now, we have only 10 minutes left, maybe. Let's work backwards to question number 5. Now, question number 5 is very clumsy. We just spend a few minutes to think about how to work on this, and I will guide you through.
該嘅分析。
This question is very clumsy. You will find that the calculation is very. You may not be able to get the answer in a short time. So I have 5 minutes left. Maybe I will just say a few words about how we can tackle this kind of question. Now, in part 1, we are asked to compute the population mean, and we are given the 5 numbers in the population. So it is very intuitive that the population mean is the average of the 5 numbers, equal to 9. Now, in part 2, we are asked to list out all the possible samples of size 3 drawn from the population of size 5. Now notice that in the question it says that we are sampling without replacement. So what does it mean by sampling without replacement? In contrast to sampling with replacement, we have different kind of sampling scheme. So if you're asked to draw 3 numbers out of these 5 numbers, just imagine that you have 5 papers written with the 5 numbers written in the paper, and then you put it in a bag. To draw 3 numbers randomly without replacement, that means you draw a paper from this bag, but you don't put it back. So that's without replacement. You don't put it back. Next time you draw from the remaining 4 paper, and then you draw from the remaining 3 numbers. That is sampling without replacement. So that if the numbers in the population are distinct, then you won't have repeated numbers in your sample. In contrast, there exists another sampling scheme called the sampling with replacement. Sampling with replacement means you also have this bag of 5 papers. After you draw 1 paper, you record the number, you put it back. With replacement, you put it back. So that every time you are drawing from the same population of 5 number. That's the meaning of sampling with replacement. And sampling with replacement will make sure that every time you are drawing from the same population, and the number you join every time are independent from each other. Now in this example, we are drawing without replacement, so that the number of possible samples we can obtain will be just the number of combination of 3 out of 5. So totally there will be 10 combinations. So there will be 10 possible samples. We just by brute force listing, we list them out. And then for each sample, we can compare the sample mean. So just imagine that if you are asked to draw these 3 numbers, this is the sample you got. Then the sample mean you have will be this number. Each of these samples will have a sample mean, and they are not the same. But now we want to determine the probabilistic behavior of this sample means. Which sample mean will be more likely to obtain, which sample mean will be less likely to obtain. So everything will be in terms of probability. So what is the probability of getting this sample? What is the probability of drawing this sample? 1/10. Yeah. Every of these samples will have the equal chance to be selected, and totally there are 10 samples. And of course, the chance of drawing each of these samples will be 1 out of 10. So this will become a typical calculation of the expectation and variance when you are given a random variable with the possible values and the corresponding probabilities. To find the expectation of the sample mean for this example is to multiply each possible value to the probability. Multiply this to this, multiply this to this, and so on. We add all these 10 products together. So this is a tedious calculation. And if you get it correctly, you will find that it's very nice. It is only equal to 9. Equal to the population mean. And it is also a mathematical fact. Okay? For this kind of sampling, the expectation of the sample mean will be equal to the population mean. So this is just an exercise for us to verify such kind of property. Now for the variance. Again, we make use of this formula. Variance of a random variable is equal to expectation of the square of the variable. minus the square of the expectation of the variance. And we already computed this as 0 to 9. So what we need will be this one. And how to get this one? Based on these two columns.
Just square root the x.
Yeah, we take the square of this column, multiply to each of this probability in this column, and add them up together. So finally, the variance of x bar is equal to the expectation of the square of the sample mean minus the square of the expectation of the sample mean. And you get this. I have seen some of you can get this answer. Okay? Now, one final remark. This number, this time, is not equal to sigma square over n. Quite contrary to what I've said before, right? In the previous question, I've mentioned about this property that when we have a random sample, the sample mean will have a variance equal to sigma square over n. But in this sample, it won't work. The reason is that we are sampling with Dow replacement. This formula works only for sampling with replacement. When we sampling with Dow replacement, actually we have another formula, a more complicated formula, which is given by this. I don't know whether we have seen this before, but probably if you didn't see this formula before, you will see it later. When we are sampling with Dow replacement, we have some correction to the formula. Where this capital N is the population size, small n is the sample size. But this is just a remark about this kind of formula. In this question, we are just asked to do this kind of clumsy calculation to get it. And you can try to work on the other part, like do the same thing, but for the median of the sample. Okay? And if you have encountered any problem about the solution, the course material, just feel free to drop me an email. So see you next week. Bye bye. Bye bye.